And we're recording. Hey, Earth Science class, good morning. Hope you're all doing well. Moving on with new stuff from the Earth Moon system type thing. And we're going to start looking at one of the most misconceived concepts in the chapter, and this idea of the cause of seasons. So I'm looking at this right here. It says cause of seasons at the top. This is in your packet. This is not going to be the assignment. Most of the time with this, we would be doing this together in class. You'd be working with a partner on this. Tough to do over distance learning. So I decided, hey, I'll go through parts of this with you, and then we'll give you a little bit different assignment with it. But the causes of seasons is one of those things that is really, really screwed up by people. So let's go ahead and just get into it. So this first section right here, we have a lovely diagram, and this is the Earth's position in space compared to the sun, obviously not to scale. And then we have these idea of distances away. So if you take a look at this, and you look at the distances away from the sun, you'll notice that we're closest to the sun in January. And if that doesn't give you pause, it probably should. The weather, of course, in January is typically winter for the Northern Hemisphere, so it's cold then. But that's when we're closest to the sun, and significantly closest to the sun. Let's find the point where we're furthest away is in July, right? So if we have 1544, right? So 154,440,000 kilometers in in July, and 148,000 in January. That, of course, is a difference. 4, 6 of a little over 6 million kilometers. That's a long way. So that should tell you something, that the difference in the distance over the course of a year is not enough to cause seasons, right? Let me say that another way. If the distance Earth is to the sun is what causes seasons, it should be warmest when it's closest, right? And we can see right here, it's not. It's warmest when we're roughly when we're furthest away. So the distance between the Earth and the sun is not the cause of seasons. That's a primary misconception about this. It does not cause seasons. So that's basically what we're talking at the first page there. Looking at all this information, discovering, hey, we're further away in winter. That can't be the cause of seasons. I want you to look at number 5 here with me. And here we have this disagreement between a couple of students. Student 1 says, I know it's hotter in the summer and colder in the winter, so we must be closer to the sun in the summer than winter. Student 2 says, I disagree. Although the distance between Earth and the sun does change throughout the year, I don't think Earth someone can't spell, always closer during summer and further during winter, so I don't believe the seasons and the change in their surface temperature are caused by the distance between the sun and the Earth. And the idea is you would debate with your partner and explain which one you agree with. Obviously, we're supposed to agree with student 2. The distance doesn't change. Okay, let's look at part 2 real quick. Here we have Earth tilting, right? And we know that Earth is tilted about 23.5 degrees. So straight up and down, 23.5 degrees. And depending on the time of year, sometimes the northern hemisphere is pointed towards the sun, sometimes it's pointed away from the sun, depending on where it's at throughout the course of the year. And it gives us information in here, and it says during the summer in the northern hemisphere, the northern latitudes could be up to 2,000 kilometers closer to the sun. Okay, and that's quite a bit, 2,000 kilometers. But compare that to our number on the other page. Compared to 6,400,000 kilometers, 2,000 kilometers, not very much. So let's think about this logically, because we're logical people. That's what science is all about, right? If 6 million kilometers doesn't make a difference, would 2,000 kilometers make a difference? No. So again, if someone says you, hey, random student, the northern hemisphere is warmer because it's pointed towards the sun and therefore it's closer, you can say it's only 2,000 kilometers closer than it normally is. That's not a big enough difference to make a difference, right? So again, because of the difference in distance because of the tilt, it's not going to cause the seasons. So what does cause seasons? We know it has nothing to do with distance. Well, let's take a look at part 3. Okay. Here we have a diagram of a spotlight and an angled piece of wood. Okay. Doesn't seem very relevant. It will. Which of these two dots, spotlight 1 or spotlight 2, would you say is more concentrated? Obviously, spotlight 1, right? So if I took a thermometer and stuck it in spotlight 1 and spotlight 2, which one would get hotter? Spotlight 1, all right? Whenever the sunlight, or the light in general, is more concentrated, it's going to produce more energy per unit area, okay? So how does this relate to the sun? We'll take a look at this. When the northern hemisphere is tilted towards the sun, that's just like the more direct light from the spotlight. So since the northern hemisphere gets more direct light, it gets warmer. When the northern hemisphere is pointed away, it's spread out more, it doesn't get as much direct light, so therefore it's colder. This is part of the cause of seasons, the amount of direct light. When it's tilted towards the sun, it gets more direct light. When it's tilted away from the sun, it gets less direct light. And of course, this is exactly flipped for the southern hemisphere, right? That's why our seasons are exactly opposite. There's one other cause of seasons, and this is under part 4, hours of daylight. I'm going to go ahead and work through this first problem with you. I realize that many of you in the summertime have no idea when the sun rises because you don't wake up until like noon. Okay, I'll let you in a little secret. During the summer, the sun will rise at about 6 a.m. During the winter, that may not be until closer to 8, and I'm rounding off. It can be, after 7, but I'm just rounding off. Sunset then in the summer can be around 9, where sunset in the winter could be again around 6. Okay, so let's think about this for hours. From 6 a.m. to 9 p.m. is going to be 12 plus 3 more is going to be about 15 hours of daylight. Again, this is when it is, hot, high summer. During winter, 8 a.m. is only, so your 8 to 8 would be 12, but I have to go 2 back from that, so it'll only be 10 hours. Do you think that makes a difference? Because it does, right? The hours of daylight make a big difference as well. During the summer, we get more hours of daylight, so we physically have more time in the sun. We get hotter. During the winter, we have less hours of daylight, so we get colder. So these two things are what combine to give us seasons. Number 1, the amount of direct light. Number 2, the hours of daylight. And these are both controlled by the tilt of Earth. So when Earth is tilted towards the sun, we get a greater amount of direct light and we get a greater hour of daylight, we get more hours of daylight. When the Earth is tilted away from the sun, or I guess more technically the northern hemisphere is tilted away from the sun, we get less direct light and fewer hours of daylight, so therefore it's colder. These two things are really what combine to give us seasons. All right, and the last thing I want to show you here is another one of these really nifty simulators from University of Nebraska. This is what's called a seasons and ecliptic simulator. and I'll kind of walk you through the parts. So here we have, the Earth and the Sun position. Of course, I should move this to today, shouldn't I? Here we go. That's about close enough. There we go. In the 20, we're in the 19th, right? Yeah. All right. Close enough. And then we can move our position. Here we are at about, we're at 10 degrees of latitude. Let's move it up to where we are, to about 40. All right. So here we have our person. Here we have our on Earth. Here we have our Sun-Earth position. And you can see right now we're kind of not pointed towards the sun or pointed away from the sun. It's like we're neither, which should make sense because the season we're in right now isn't the hottest one nor the coldest one. It's the one in between, all right? So when we talk about Earth's position in space, as we move this, there's going to be a point, and you can see the little sun. I pointed. That doesn't help you at all. You can't see what I'm pointing at. You can see the little sun position over here on this diagram slowly moving upward or northward as we move through the course of the year. And you can see right at this point right here, when the northern hemisphere is pointed towards the sun is at its highest point on Earth. That's right above this line right here, which those of you who know globes, that would be the Tropic of, let's see here, Capricorn or Cancer? Cancer is the top one. So this is the Tropic of Cancer, and that is the northern edge of the tropics. Okay. Let's fast forward 6 months. There we go. That's about as good as I can get. And you'll notice, oh, hey, now the sun is as far south as you can get. That's over the Tropic of Capricorn. And you'll notice that, hey, we're not getting much for direct sunlight, right? If you look at here, we can see, oh, that sunbeam is really spread out. It's a very low amount of sun. So this should make sense, right? During our winter time, when it's December, you can see that the sun is furthest south. We're not getting much direct light. In fact, if you go up to the North Pole, you're getting no light at all. Go back to about 40. So you can see that this amount of sunlight and this directness of sunlight is what really makes the difference for seasons. Talking about points on the globe, the point where we're pointing directly away would be what we call the winter solstice, right? The point where we are pointing directly towards would be the summer solstice. We have two other important days through the year, and those are called the equinoxes, right? So when we're exactly halfway, notice the sun is directly over the equator, and completely half the world, this right-hand half, is in daylight, and this dark-hand half is in night. So we have equal night. Well, if you know a little Latin, equal night means equinox. That's where the word actually comes from. So during the equinoxes, we have exactly half the time spaced out. We get exactly half the amount of daylight, half the amount of darkness. It's the nice medium point. So here we have the fall or the autumnal equinox. And then, of course, in the other side, we would have the spring or the vernal equinox. All this stuff is in your book. Your assignment will be posted on the classroom page. Just a little bit of discussion about equinoxes and that kind of stuff. So hopefully you got this figured out. If you have any questions, as always, let me know. Have a great day.